Okay, so the lesson for today is going to be on a concept called mapping notation and reflections. It's really going to build on that idea that we covered yesterday where we were moving things left, right, up, and down. But we're going to really run with it today, especially with that whole mapping notation idea. You'll see what I mean in just a second. Let's get going. So today's plan, first of all, last class, like I just mentioned, we looked at moving functions left, right, up, and down. Basically, we looked at it under this idea that there's a function notation that looks like this, where you are changing something inside the function. So you're replacing the value of x with an x minus h. And then on the outside of the function, you're adding some k. Now, the whole purpose of h is if you see x minus something, so if it was like x minus 4 on the inside of the function, you'd be moving that object to the right. Whereas the purpose of the k value, if you have, let's say, plus 5, that would be moving it up. So horizontal translations occur inside the function, whereas vertical up and down transformations occur outside the function. We'll get some more review at that today, but before we get there, we're going to start by looking at a super useful way of describing how to move a coordinate, so in other words, an x and a y, to its new location after moving the entire function left, right, up, and down. So in other words, in plain English, we're going to learn how to basically move one coordinate at a time given some sort of transformation. So we'll move one coordinate at a time. This, by the way, this method we're going to learn today, it's called mapping notation. Super useful stuff. Also, in the second half of class today, we'll introduce reflections. This is where you're flipping the function across the x or y axis. We'll talk about reflections in function notation, but also in equation notation, and we'll also do some sketching. Anyway, that was a long rant. Let's get going. So first of all, mapping notation. Mapping notation is a way of representing a function that shows what actually happens to the x and the y components of the coordinates of the original base function. In other words, we're showing what you're actually doing to an original xy. So if you had some coordinate xy on your original base function, we're going to be talking about what you'd be doing to that to move it to its new location. So it's got a new location, a new coordinate, no longer the original x and y. It's moved somewhere else because you've moved it left, right, up, or down, right? Best way of looking at this is through an example. So in the translation of y equals x squared, that's our base function, into y equals x squared plus 4, the graph has moved 4 up. Well, this, of course, shouldn't be a surprise because we're adding 4 to the outside of the function, right? Now, that means the y values on the original are increased by 4. So what this would look like in mapping notation, since we're moving, like if this was the original graph right here, we'll say, if that was the original graph, all we're doing is we're moving that original graph up by 4. So maybe now it looks something like this. You know, we've moved it up 1, 2, 3, 4 places. So what we're doing to each an individual coordinate here, so to each of these coordinates you'd have, is we're just increasing the y values by 4. So in mapping notation, what this is going to look like, we always start by saying xy, and then we draw an arrow. So it's saying xy is going to become, now think of it this way. If we're moving the graph up 4, do you think we're actually moving our x values left and right? I sure hope not, right? We're not moving it anywhere. So in other words, x is just going to stay the same. Our y value, on the other hand, we're increasing our original y values by 4. So we could say that this is y plus 4. And then that's it. That's mapping notation. So what mapping notation shows is it just shows that since we've said we are moving the graph up 4, all that means we're doing is taking the y values and increasing them by 4. We're not touching the x values, so the x values would stay the same. We're just moving the y values up by 4. Now, the reason we care about this, I know I didn't put it in the notes, but the reason we care about this is, suppose we know on the original function, we knew the coordinate 3, 9. So when x is 3, y is equal to 9. On the new function, x squared plus 4, this is just going to move this coordinate up by 4. So 3 is still going to stay the same, but we're going to have to go 9 plus 4, which would be 13. So the new coordinate location of the original location 3, 9, it's been moved to now 3, 13. That's just mapping notation. Okay, moving on. All right, what about this one? What is the mapping notation for y equals x minus 3 squared? Well, let's think about what kind of a transformation this is. Notice, first of all, that this is on the inside of our function. If there's a transformation on the inside of our function, does that move it left, right, up, or down? Well, hopefully what you just said to your screen right now is it moves it to the right. And the reason being is because x minus something inside the function, that moves it to the right. If it was x plus something, it'd be moving it to the left. So we can say that this is moving that function right 3. So what it's really doing is it's just taking our x values and moving them to the right by 3. Now here's where things get really, really funny. If you are taking an x value, like let's say you had the coordinate, let's say that was 3, 2, and you're moving that right 3, the new location of that thing is 6, 2, right? So since we moved it to the right by 3, the x value increased by 3. So what's interesting about this is, even though inside function or equation notation, we have a -3 to indicate a right, when you put this in mapping notation, our xy is actually going to become x plus 3, and then y. This is because in mapping notation is showing you exactly what is happening to each of your coordinates. When it's in function notation and equation notation, it's not showing what's happening to the coordinate. It's just working around how the algebra is going to work out in the problem, right? It's very strange that this is a minus and then it moves it to the right. I understand that, right? It is just what it is. Mapping notation kind of brings you back to reality, though. With mapping notation, you can see that your x values are just increasing by 3, which is moving them to the right by 3. Definitely a weird hurdle. Personally, I greatly prefer mapping notation over any of the other notations we have. I think this is awesome. It really makes it clear what's going on. But of course, function notation and especially equation notation, they're also really important as well. Now, mapping notation, the reason we care about this is it's just a way for you to compare corresponding coordinates on the original function versus the transformed function. So what it's really useful for is transforming a shape one coordinate at a time. So for a transformed function in the form y equals f of x minus h plus k, so in other words, a normal function notation, the mapping notation that corresponds to this would be xy becomes x plus h, and then y plus k. The y isn't really a big surprise, right? Remember even before when we learned about this, I said, oh, if you're adding 7 on the outside, clearly you went up by 7. It isn't a huge surprise, right? So again, like I said, this is particularly effective when transforming shapes, just like the figure to the side. So in something like this, if we wanted to talk about what its mapping notation would be, let's assume the one down here, the black one here, is the original. And then this blue one here with all the little apostrophes near it, let's assume that is the new shape. Well, if we just compare one coordinate at a time, we can see that this letter right here, this vertice right here, it moved up 1, 2, 3, 4 up. So it went 4 up, and then it went left 1. And that put it into its new location. And you could test all the other ones, but you'd see it was 4 up, left 1. So what this would be in mapping notation, I know it's not necessarily asking, but maybe it's just nice to note. We could say xy is gonna become x. Since we're moving left 1, we're subtracting 1 from it, so it's x minus 1, and then y plus 4. This horizontal stuff, like in the x direction, this is always a hurdle. People always complain about this because, you know, in function and equation notation, minus meant going to the right and plus meant going to the left. But in mapping notation, it's back to how, at least I feel my brain thinks it should be, right? So x minus 1 is actually moving it to the left. Really weird. It's definitely just a hurdle that you have to go over time. Practice definitely evens this all out, but you know, it is what it is. So here's an example. Write the mapping notation for f of x equals absolute value of x plus 2 minus 4, and then complete the table. So let's start with the mapping notation there. Before we do that, let's at least figure out what on earth is going on with this function. If we kind of strip away all the weird stuff that's happening to this function, namely this plus 2 and this minus 4, you can see that our base function is just simply an absolute value of x. Since our base function is just an absolute value of x, think about what's happening inside the function versus outside the function. Inside the function, we have x plus 2. Now, don't get confused with the mapping notation we've done today. Just think back to what we see in normal equation notation. If we have x plus 2 inside the function, replacing our x, what direction is that moving? Well, hopefully you're realizing that's actually moving it to the left. So this is moving it left 2. And this minus 4 on the outside, I always find the outside ones way easier to work with. Minus 4 on the outside means we're moving it down 4. So since we're moving this left 2 and down 4, we can get our mapping notation going. This is going to be xy becomes, let's see, if we're going left 2, that's x minus 2. And then if we're going down 4, I guess that would be y minus 4. Now, the reason we care about mapping notation will become very clear in a question like this, where we are literally taking coordinates from the original base function and we are moving them to the new transformed function. Probably the easiest way of doing this, in my honest, humble opinion, is just take these coordinates, plug them into your mapping notation, and that'll show you where they've moved to, right? A common misconception that people have is they say, oh, it's just a matter of just plugging in your x into this. That's not necessarily the same point. These points have shifted. We need to account for that. So anyway, what we'll do is we'll take our original xy and we'll plug it into this mapping notation and see where each of our coordinates have moved. So in this first case, negative 2, 2, it's going to be negative 2 minus 2, which is negative 4. And then it's going to be 2 minus 4, which is negative 2. So this original coordinate, negative 2, positive 2, is moving to negative 4, negative 2. You can continue this with all those other points there. So if we plug in negative 1 into this, we're going to get negative 3. And if we plug 1 into this, we're going to also get negative 3. That's kind of a nice coincidence. If we plug 0 into this, we're going to get negative 2. And if we plug 0 for y, we're going to get negative 4. If you plug 1 into this, you're going to get negative 1. And then 1 into this one, you're going to get negative 3. And the last one here, if we're going to plug 2 into this, 2 minus 2 is 0. And if you plug 2 into this one, 2 minus 4 is negative 2. So that'll hopefully be a very useful way of seeing that you're just moving the whole function 1 point at a time. Mapping notation is brilliant, especially for that case before where we had a shape that we wanted to transform. That really, honestly, is what mapping notation was pretty much designed for. Anyway, let's kind of change our focus on this now. We're going to look at a review of translation. So this is going to be more a review of what we did last class. So we're flipping back a little bit here, right? So the first question here is asking, identify a base function and state in words the translation that's occurred to that base function to get the following function. So basically, we want to kind of strip away the nonsense from this and figure out what our base function could be. There was a whole list of base functions I provided last class, but I think the obvious one in this case would probably be x cubed being your base function. We might as well call that y equals x cubed, just so it looks a little bit better, so it's not sitting on its own. Doesn't really matter. But anyway, that's going to be our base function. If that's our base function, notice we changed the inside of the function to x plus 5, and then we stuck a minus 7 on the outside of the function. Well, if we change the inside of the function to x plus 5, in words, what that means we're doing is we're moving it left 5. And since we did a minus 7 on the outside of the function, that means we're moving it down 7. I think that's about it. That's all we really have to do on this one. So again, we identified a base function, so something that you could compare this to, and then figured out in words a translation that occurred to that. All right, next one. This one's a bit of a challenge. Consider the function f of x equals x minus 4 squared minus 2. Suppose it is transformed into the graph of g of x equals f of x plus 1 plus 3. What are the coordinates of the vertex of y equals g of x? Well, holy smokes. Okay, this one is a tough one. So this is one of the rare cases where you're going to see a question where our base function is not something simple, just like plain old x squared. You might look at this f of x and say, oh yeah, if you stripped everything away here, you'd just be left with an x squared. But keep in mind, this question is saying that that f of x, this one right here, is being transformed into a new graph like this. So what I'm going to do first, since we're looking for the coordinates of our vertex of this new function, maybe I want to start by figuring out what my vertex is of this function. Well, a couple different ways of doing this. If you're someone who's pretty keen, and you might remember back in Math 20-1, we learned about vertex form of a quadratic. You might be able to pick it out from that. But if you don't see that, I wouldn't blame you. If you don't see that, you could see that this original f of x here is just in itself a transformation of x squared, where we moved it right 4 and down 2. Now, the vertex on an original x squared function would just be 0, 0. But if we're moving that right 4 and down 2, that moves the vertex now to 4, negative 2. So that is the f of x vertex. It would be 4, negative 2. We moved it right 4, down 2. That's where our vertex would be. What we're looking at on this function is we're seeing that we have an x plus 1 and then a plus 3. Now, if you put this into words, it might make it a little clearer. What g of x is doing to f of x is it's moving f of x left 1 and up 3. So left 1 is because of this inside stuff here. Up 3 is because of this outside stuff here. Now, if we took the coordinate 4, -2, maybe it helps to draw a picture. If we took the coordinate 4, -2, and we moved it left 1 and up 3, think about where it ends up. Well, if we moved it left 1, that moves x down to 3. And if we move this up 3, that moves it up to 1. So it would be the coordinate 3, 1. And I would say that is accurate. So the vertex of g of x, that would be the coordinate 3, 1. Whew, that was a tricky one. That was a really tricky question, actually. So the whole idea here is figure out what your transformations are and where you are moving it and how that goes, right? All right, this next one is an absolute beefcake. So buckle up. This one's an even bigger challenge. This one stumps people all the time. If you really want to pause the video here and give it a try, see if you can get it, that would be awesome. But otherwise, I'm going to go over it right now. So if y equals the square root of x, find what horizontal translation would be applied so that the translated function will pass through 17, 8. So in other words, you plug in x is 17 and it'll spit out y is 8. This is a weird one. Here's what I'm going to start with. Notice the question is just asking what horizontal translation would be applied. That means we need to assume that there is not going to be a vertical translation. We're just moving it horizontally. Since we're moving it horizontally, we can say we're doing a translation that'll look like this, f of x minus h. That's a horizontal translation. Now that's in function notation. We actually have an equation for this. So let's turn this into equation notation real quick. In equation notation, we just need to replace our x with an x minus h. So this gives me y equals the square root of x minus h. Now here's what's funny about this one. Since we know y equals x minus h, or the square root of x minus h, and we're trying to figure out what that horizontal translation will be, we just need to take a coordinate that we know, namely the 17, 8, plug it into here and figure out what on earth h could be. Bear with me on this one. We know x is 17, we know y is 8, so let's plug in 8 is y equals the square root of 17 minus h. We want to solve for what h is here. The square root is kind of causing us some trouble. We need to get rid of that square root somehow, so I would recommend squaring both sides. So if you square both sides, that gets rid of our square root. This will give us 64 equals 17 minus h. And then this becomes just a big switcheroo. You can add h on both sides, so h plus 64 equals 17. And then minus 64, and we have h equals negative 47. So think about what this means for a second. This means inside this function, we had x minus negative 47 right in here, right? Now, x minus negative 47 is the same thing as saying x plus 47. So what kind of a horizontal translation do you think that is? It's got 47 involved in it somehow. What do you think the plus represents when it's inside of a function? Well, that represents it's going to the left. So the answer to this one is we moved this function left by 47. That is a really hard question. The whole idea here is we have to take advantage of the fact that we knew it was only a horizontal translation. We had to assume that there wasn't a vertical translation. And since there was only a horizontal, we can say it's x minus h, and then plug in an x and a y, and we're golden, right? That's about as tough as these questions get. Obviously, I bet if you're scratching your head at that, just means you basically need to get a little bit more practice in. We're going to learn the next thing of the lesson today. It's going to be a bit longer here. We're about halfway through. Let's get rolling. So moving away from mapping notation and that review of translations, we're going to talk about something completely different today. We're going to talk about reflections. So I want us to first consider a triangle on the following grid. Now it says label the vertices as A, B, and C, and then use the x-axis as a line of reflection and plot the new vertices A prime, B prime, and C prime. Okay, so it doesn't really matter which one is A, B, and C, so it's really up to you, but I think I'll do this one is A, and I'll say this one is B, and I'll say this one is C. Again, it doesn't really matter which one's which. You kind of have freedom to do so there, right? Now it says, then use the x-axis as a line of reflection and plot the new vertices. What that means is we want to use this x-axis as if it was some sort of mirror, right? So we're crossing this over and we're flipping it over to the other side. Well, the easiest way to do this is just to count how far away from the x-axis each of your points are. So this first one, this point A, is 7 points away from the x-axis. So on the other side, when we cross and reflect over that x-axis, we still need to be 7 points away from it. So we're going to be down here, and I'm going to label that A prime. Same idea with these other ones. B is 8 points away. So if I start here and go 8 points away, that's going to put us right there. And I'm going to call that B prime. And then the last one here, C, is 3 points away. So I'm going to move it 3 points away this side, and I'm going to call that C prime. Now it does say plot the new vertices. I think it's probably a good measure just to draw the full triangle as well. So I'll just connect those sides. If it's a little messy, forgive me. If you have a straight edge, it's probably a little bit better. There we go. Awesome. So awesome. Now the question's asking, how are the coordinates related to the original triangle? Well, let's see here. Let's look at the coordinate of A. The coordinate of A is 1, 7. The coordinate of A prime is 1, -7. Interesting. What about B? The coordinate of B is 5, 8. 5, 8. The coordinate of B prime, well, that's going to be 5, -8. Very interesting. What about C? The coordinate of C is 7, 3. The coordinate of C prime is 7, 7, -3. So how are the coordinates related to the original triangle? Well, the answer to that is the y value multiplied by -1. So all you did was you multiplied the y value by -1. Your x value, on the other hand, the x value just stayed the same. All right, so that was a flip across the x-axis. So we're flipping vertically across our x-axis. We just multiplied our y value by 1. What if we flip the other way, though? What if this time we're using our y-axis as a line of reflection? Let's plot the new coordinates A double prime, B double prime, and C double prime. So once again, I'm going to say this is A. We'll say this is B, and this is C. If I'm flipping them over the y-axis this time around, A is just going to move one distance away from the y-axis. So A prime is going to go right here. A prime. B looks like it's 5 points away, so I'll move it 5 points away from the other one. I'll call that B prime. And then C looks like it's 7 points away, so I'll move it 7 points away over here. The same height, you'll notice. That is C double prime. I forgot, these are double primes, my mistake. Some of you are probably screaming at the screen there. Holy smokes. All right, anyway, connect the lines on these ones. So here we go. There we are. And there we are. Perfect. So we used the y-axis as a line of reflection. We mirrored it over, so that was a horizontal reflection. Now, how are the coordinates related to the original triangle this time around? Well, I bet I don't have to show you literally every single one. Let's look at the first coordinate. The first coordinate was 1, 7. The coordinate of A double prime, however, is -1, 7. You probably already see the pattern, so I'll save you the trouble. If you really wanted to compare each one, go for it. But how are they related? Well, this time around, the x value multiplied by -1. So when you are flipping across the x-axis, like we did on the last example, like on this slide, you're multiplying your y value by -1. And you can think of that as being a vertical reflection. So you're changing it vertically. The y value deals with vertical, so that's why it's a vertical reflection. On this one, however, since we're flipping over the y-axis, that's a horizontal reflection. And since it's dealt with in a horizontal direction, you're going to be messing with your x value. So your x value is what multiplies by -1s. All right. So just to summarize that, for a given base function f of x, a vertical reflection, so an up and down vertical reflection, across the x-axis occurs when y equals -f of x. So in other words, it's where you are multiplying your entire base function by -1. If you wanted to flip this around, really what's getting multiplied by -1, because if I like divide by -1 on both sides, you could say -y equals f of x. In other words, your y value is what was being multiplied by -1 in that case. Really, it just is a matter of perspective, that's all. As for a horizontal reflection, this is across the y-axis, and this occurs when y equals f of -x. Notice a horizontal reflection happens inside the brackets, just like a horizontal translation happened inside the brackets. So with this reflection, only the input gets multiplied by -1. So you replace all of your x's in your original function with -x instead. Okay, so we got a couple graph questions. If you don't have more than a couple colors of pens, you might actually want to pause the video here and go get some. If you don't have them though, like period, like even if you look for it, I guess you won't need to worry about it. So on the following grid, graph the function y equals x squared minus 4x. This will serve as our base function. So I'm going to start with that first. I'm going to do that in red just so it sticks out. Now, for some of you, it's probably been a while since you've graphed something like this. This is a quadratic right here. It's an x squared function. If this was just straight up x squared, that's usually pretty easy to graph. But this one's got some other stuff going on to it. It's a little bit more complicated. So just a refresher from Math 20-1. If you ever have a quadratic and you want to graph it, it's always a good idea to start by finding its vertex. And the vertex of a quadratic comes from the formula x equals negative b over 2a. For some of you, it's been a long time since we dealt with this, so I wouldn't blame you at all if you had forgotten about that, but it just is what it is, right? So I'm going to plug in negative b over 2a here. Negative b in this case is going to be positive 4 because negative 4 is positive 4. Just by the way, in case you're wondering where I'm pulling that from, y equals ax squared plus bx plus c. That's a standard form of a quadratic. So the number in front of the x squared is called your a, the number in front of your x is called your b, and the number on its own is called your c. So when I say negative b, I'm really talking about negative the number in front of x, which is negative 4. So negative 4, positive 4. Anyway, over 2 times a is the number in front of the x squared. Looks like there's just a 1 there. So 4 divided by 2 times 1. Well, 4 divided by 2 times 1 is just 2. So that tells me my vertex is that x is equal to 2, somewhere along here where x is equal to 2. To find where that is exactly, we just need to plug 2 into our original function again. So I'll say y equals 2 squared minus 4 times 2. This is going to tell me my y value of my vertex. Well, 2 squared is 4. 4 minus 4 times 2 is 4 minus 8. That's going to be negative 4. So my vertex is at 2, negative 4, right down there. To finish graphing this function, remember, once you have your vertex, you can use something called the 1-4-9 rule. This says when you start at your vertex, go over to the right by 1, and then up 1 times a. Well, a is 1, so I'm only going to go up by 1. Then return back to your vertex, go over 2 points, and then go up 4 times a. So that's part of the 1-4-9 rule. So go up 4 times a. Well, that'll take us up to here. And then go back to your vertex and go over 3 points this time, and then up 9 times a. So that's going to bring us all the way up to here. Now, of course, because this is a quadratic, we want to make sure that it is symmetrical on both sides. So I'll put another dot here, I'll put another dot here, and I'll put another dot over here. And then I will connect all of that with a line. There we go. Almost there. It's not looking super great, but you get the idea. Nice. Okay, so next part, it says graph the mirror image in the x-axis. Okay, so the x-axis, that's going to be a vertical reflection. I'm going to do this one in blue. So if I'm graphing this as a mirror image across the x-axis, I just need to flip all these coordinates up over that x-axis. So I'm going to start way down here at the bottom where the vertex is. The vertex 2, negative 4, if that's going to flip over the x-axis, that's going to become 2, positive 4. Same with these 2 points here. This is 3, negative 3. Well, this is now 3, positive 3. And this one is 1, negative 3. This is going to become 1, positive 3. Now, these 2 points right here are on the x-axis, so they're not going to move. But these ones, they're going to have to flip down below. So this is going to go all the way down to negative 5 here. And this one up here is going to go down to negative 5 down here. And then hopefully you can see that quadratic shape coming along. Do my best to draw that. Again, it's not perfect, but you get the idea. Oh, definitely not like that. Hold on. You get the idea, though. That's really the main thing. That's all we really need to know there. Wow, that ended poorly, but you know, I'm going to ignore that. All right, so what would the, or rather, what equation would model this? Well, if we're graphing this as a mirror image across the x-axis, this is what we call a vertical reflection. Now, a vertical reflection is where your entire function gets multiplied by negative 1. So you can say y equals negative, and then in brackets, x squared minus 4x. Now, having a negative on the outside of a bracket is kind of unsettling to you. You can always double dip that negative through. So this would equal negative x squared, and then negative 4x is plus 4x. So either of those functions there, that would work just fine. Next one here, we're going to graph the mirror image across the y-axis. I'll do that one in green. So back focusing on our red, we're going to be flipping the red function over the y-axis. So that's going to move this over here. This point here is going to move here, whereas this one's going to move way over here. This point is already on our y-axis, so I'll just leave it still, but this one is going to flip from 4 to -4. This point here, it's going to flip over our y-axis. It's not going to move too far. It's just going to move here. This one, on the other hand, it's going to move way over, so it's 5 away from the axis on the other side, so it's going to move over there. One more time, let's connect these with a line. There we go. There we go. There we go. Keep on going. Do the best I can. There we are. Whew, and there we are. We've graphed the mirror image of the red function across the y-axis. So these ones are a little sneakier in terms of an equation. So what equation would model this? When you are flipping something across the y-axis, you have to replace every x with a negative x. So in function notation, that looks like f of negative x. Now, if we look at our actual function here, we just need to replace each of these x's by a negative x. So be careful as you do this. This is going to be y equals negative x squared minus 4 times negative x. Now this just looks really uncomfortable, so it is what it is. I'm going to leave this alone though. Negative x squared, I'll just leave that fine. I think you would see if you went negative x times negative x, you'll probably just get positive x squared, but I'll just leave it for now. As for this one though, negative 4 times negative x, that's just going to be positive 4x. So that right there, that represents the mirror image in the y-axis. Whew, okay, I think we're beating this to death. We got another page or so to go here. Let's keep on rolling though. So this next example, given the graph of y equals f of x, that's that weird blue squiggly line thing there. Believe it or not, that is our function. Draw the graphs of y equals negative f of x and y equals f of negative x. Okay, let's take some time on this one. I'm gonna switch back to red. I'll do this one right here in red. Notice the negative is on the outside of the function. Do you think that's going to be a vertical reflection or a horizontal reflection if it's on the outside of the function? Well, hopefully you recognize stuff that's on the outside of a function, whether it's a negative or whether it's a plus, that's going to be a vertical movement. That means this one here is going to be a horizontal movement, right? So for this first one, and I'll do it in red, we're going to vertically reflect this, which means we are vertically reflecting it across our x-axis. So our x-axis is what we're going to be flipping this across. So move each point individually one at a time. This point right here is going to flip down to here. This next point up here at 6 is going to flip down here to -6, and I'm going to connect those two just so I don't get lost. This point right here is already on the x-axis, so it's not going to move at all. I'll connect those points again so I don't get lost. There we go. This point needs to flip above. It's going to flip above to here. And again, I'll connect those points. And then this one right up here needs to flip across, so it's going to go down to -4. And I will connect those dots. Nice. So before I graph this other one here, for this function, did we notice any points whose coordinates did not change? In other words, were there any points that when we applied the reflection, those points didn't move? Well, there actually was one. There was this one right here. Now think about why that one didn't move. When we flip it across the x-axis, why did this point in particular not actually move? Well, the answer is pretty simple. It didn't move because it was already on the x-axis. So we can say for any points that whose coordinates did not move, we could say the point 1, 0 didn't move. And again, that was because when you multiply the y value, which is just 0 here, by -1, it doesn't do anything. So it's not actually flipping it anywhere. Now, there actually is another point that didn't move. It wasn't an exact dot, but see this point right here at about 3, 0? 3, 0 also didn't move. So it's important that we acknowledge that one as well, because that one still, while it wasn't an official point that we had to plot, it still is another position that didn't move because it was on the x-axis. All right, next one we'll do. I'll do this one in green, the horizontal reflection. So that's f of -x. So we're going to be flipping our function the other way this time around, but it's going to be basically the same idea. I'm going to start with this point on the far left here. It's going to be moving over to 3. So that point is now done. Then I'll move the next point. Well, that one's actually already on our y-axis. If we're flipping across our y-axis, that point's not going to move. I'm going to connect those with a line just to make sure we don't lose them. Then we have this point here. If it's flipping across the y-axis, it's just going to move over here. So it didn't exactly budge too far. Connect it with a line. We don't want to lose it. Next point would be this one, flipping it across this way. That's going to move it over to here. Connect that with a line. And then the last point that we have to draw is this one right here. Well, if it flips across the y-axis, it's going to go way over here. And then connect that with a line. That was miserable. Try that again. There we go. Okay, awesome. All right, so that was kind of a train wreck. It looks like a total jumbled mess right now, but it is what it is. But if you can focus just on the original blue graph and this green graph we drew, were there any points where the coordinates did not actually change? Well, there was certainly one coordinate. It was the one right here at 0, 6. So 0, 6 didn't move. And the reason it didn't move is it was already on the y-axis. In other words, x was already 0. If you're multiplying x by -1 to get a horizontal reflection, 0 times -1 doesn't do anything. It didn't budge it. Hopefully that makes some semblance of sense. We have one last page. This page should not take nearly as long. Here we go. Doesn't look like we're having to draw any graphs or anything on this one. So for this first example, if f of x equals x plus 3 squared minus 2, it says sketch and write the equation for each of these following. Now I'm just going to tell you right now, I don't want us to sketch it. So just cross out where it says sketch. We're just going to worry about writing the equation for this. So this first one here says y equals negative f of x. That just means you take all of f of x and you multiply it by -1. That's it. That's all you got to do. So we literally can just write y equals negative, and then in big brackets here, x plus 3 squared minus 2. Maybe I'll make those brackets bigger there to make it match. That's it. That's honestly all you have to do. If you want to be even fancier with this, by all means, you can be. You can take this negative and just bounce it here. So this would be negative x plus 3 squared. And then the negative would also bounce to the -2. So it would make it plus 2. That's about as far as we can go with it, though. Don't go thinking that you can take this negative and bounce it inside the brackets here. This squared kind of stops you in the tracks there. This is something totally separate. So we can't go any further there. That one is all well and good. Now, as for this other one, y equals f of negative x, this one's going to be a little more interesting. We have to replace every x we see with a negative x. Now, the good news is in this question, there's not very many x's to be changed around here. So what we're actually going to have is f equals, instead of saying x plus 3, we have to say negative x plus 3, and then squared minus 2. That's actually all we got to do on that one. There's no more cleaning up we can do on that. That's actually it, right? So that would be our horizontal. That's our horizontal reflection, whereas this other one would have been our vertical reflection. Really important to know the difference there. Last question before we get to our summary. Sorry again for such a long video, 38 minutes. It's kind of killing me here too. The graph of y equals f of x, where f of x equals the absolute value of x plus 4 plus 1, is reflected in the y-axis. Okay, I'm going to pause right there. That's actually a horizontal reflection. Make note of that. It's easier, at least in my mind, to think of it as a horizontal than across the y-axis, but whatever floats your boat. So it's reflected in the y-axis, that's horizontal. This produces the same results as would translating the graph to the right by how many units? Okay, so this is a really interesting one. I think it would be for our best if we drew a little sketch of what this graph looks like. Before we graph a sketch of what this function looks like, think about what the base function would be here. If we stripped away all the nonsense, I think we'd agree that a base function here would be the absolute value of x. And the graph of the absolute value of x kind of just looks like a big V shape kind of thing, right? Now, think about what this x plus 4 plus 1 is doing. This plus 4 on the inside of the function is moving it left 4, whereas this plus 1 on the outside of the function is moving it up 1. So we're just taking this pointy function here and we're moving it to the left by 4 and we're moving it up by 1. So what this is going to look like, if I were to draw a very rough sketch of this, if I took this V-shaped and moved it to left 4 and then up 1, it's going to look something like this, right? So I moved it left 4 and up 1. Now, if we are doing a horizontal reflection, so if we're reflecting it this way, this would produce the same results as would translating the graph to the right by how many units. Well, think about what this would look like if we flipped it over. Notice the little vertex right here is 4 away from our y-axis that we're reflecting across. That means when you reflect to the other side, it's still going to have to be 4 away, but this time it'll be at a location of +4. So it'll look something like this over here instead. That was miserable. It doesn't even look like it matches at all. What about this? There we go. That's a little bit better, right? Bottom line is, when we reflect this across our y-axis, because this graph was already symmetrical, it's going to remain looking symmetrical when it makes its way to the other side. So this is going to produce the same results as would be if you had literally just shifted the whole thing to the right by how many units? Well, if it went from -4 to +4, that would be 8 units, right? So 1, 2, 3, 4, and then 5, 6, 7, 8 units. Okay. So just kind of another trick question. Sometimes a horizontal reflection can actually end up looking exactly the same as just a horizontal shift, especially if the function was symmetrical to begin with. Whew. All right. So final slide. So just to summarize all the million things that we've done today, let's summarize this up in this nice chart. So we're going to focus on this first row first. If we have a reflection across the x-axis, so again, this is our x-axis, this is our y-axis. If we're reflecting across our x-axis, the type of reflection that is that's a vertical reflection. Now in function notation, what that means is if it's a vertical reflection, that means we're multiplying the outside of the function by -1. So it's y equals negative f of x, because we're multiplying the outside of the function by -1. In mapping notation, this is one of the first things we did today. You're just taking your original xy and you're moving it. If you're doing a vertical reflection, you're moving it such that your x does not actually change. So x just stays as x, but your y gets flipped over and multiplied by -1. So it's going to be negative y. And again, the reason for that is, imagine you have like a point up here at the coordinate 5, 4. If you flipped it vertically, that's now at the coordinate 5, -4. So you just multiplied your y value by -1. Now, the last column here, invariant points. Are there any invariant points if you're flipping across the x-axis? Well, of course there would be. It'd be anything that's already on the x-axis. If something is sitting on the x-axis and you're asking it to be reflected across the x-axis, it's not going to move. Now, the things that sit on top of the x-axis, they have a special name. They're just called x-intercepts. That's it, right? So your invariant points will just be your x-intercepts. Now, looking at a y-axis, maybe this one will go a little quicker. If we are reflecting across the y-axis, that's going to be a horizontal reflection. Likewise, if we're dealing with function notation, because it's horizontal, that's going to happen on the inside of our function. So this is going to be y equals f of -x, because it's a horizontal reflection. Horizontal stuff always happens inside the function. In mapping notation, we could use this coordinate 5, 4 again. If you're doing this across the y-axis as a horizontal reflection, this moves that coordinate to -5, +4. So in other words, your mapping notation says move your original xy to a new position where you have -x, +y. So y doesn't change when you do a horizontal reflection, but x gets multiplied by -1. And then take a real wild guess at what this invariant point would be. If you're flipping across your y-axis, what points are invariant? What points aren't moving? Well, those would be your y-intercepts this time around, right? Holy smokes, that was a lot of information. We covered a ton of information. That was a over 43-minute long video. I apologize, but we do have a little bit more work we got to get done, of course. Practice does make perfect. You can try page 28, questions 1, 3, 4. You can do those questions from last class on page 12. Or if you are a student in class, of course, you can have the chapter 1 assignment booklet. That one is not going to be due for a little while here. It'll be due before our first quiz, but it is what it is. Anyway, as always, if you need any extra help, please let me know.